Good afternoon, ladies and gentlemen. So this particular video is going to talk about the last couple of FRQs that I kind of sent out the other day. So hopefully you've had a chance to work through FRQ 3 and 4. I'm going to post the key to these a little bit later, but for right now, let's just kind of go through and talk about what's going on. So if you haven't had a chance to, pause the video right here, try and work through FRQ number 3, and then once you're ready, unpause it, and let's get rocking and rolling. So this third FRQ is focused on an experiment where I have two carts and they are being set up so that they're basically going to have the same velocity and they're going to be fired at each other and they're going to crash at some point. All right, and we do it 3 times and we set the collision to do something different each time. Now, in each trial, it defines what happens after the collision. So trial A, it says the two carts come to rest after the collision. Trial B, the two carts bounce off each other and exchange velocities. And in trial C, the two carts bounce off each other and move with lower speeds than they had before the collision. All right. Now, what our answer needs to be is that basically we want to identify the 3 types of collisions that are going on here and kind of explain why we picked that. So it says in a paragraph length response, basically all you need to do is identify for trial A, trial B, trial C, what's going on and give an explanation for it. So if you've had a chance to go through it, let's kind of break down the 3 different collisions here. So we'll start with trial A. Trial A says that I have 2 carts that come to rest as a result of the collision after they run into each other. So right away, we can tell ourselves that there's a loss of kinetic energy. Now remember, when we talk about collisions, there's 2 things we look to see is conserved. We know momentum has to be conserved in every collision. And we try to see if kinetic energy is conserved as well, because that can govern what type of collision it is. In this case, it clearly is not conserved because they come to a rest, so they stop. So in this case, it's not an elastic collision, which means we're left with inelastic and completely inelastic. Now, because the 2 carts are sticking together, remember we talked about this with collisions, this means that this is actually a completely inelastic collision because it loses the most kinetic energy of all the collisions here. So in trial A, it's a completely inelastic collision. And you can see right here, kind of my explanation. Something similar, if you wrote that down, was perfect for this answer. All right. Now for trial B, it says the 2 carts bounce off each other and exchange velocities. Now the carts are exactly the same. They're the same mass and they have the same launch velocity. They're just going towards each other. So this means that basically they bounce off and they start going the other way at the exact same velocity, just with opposite signs. Now whenever you kind of read something like this, if I hear something along the lines of that exchange velocities, they're trying to tell you something. And in this case, if I exchange velocities and it doesn't seem like I lose any speed, this is suggesting to me that it sounds like kinetic energy is conserved in this collision. And the only collision where that makes sense is an elastic collision. So for trial B, because the 2 carts bounce off each other and exchange velocities, kinetic energy is not lost. Therefore, this is an elastic collision. All right. Now for trial C, the last piece of this, it says the 2 carts bounce off each other and they move with lower speeds than they had before the collision. So they basically bounce off and start, going the other way, but they're not moving as quickly as they did before. So right away, velocity drops. That tells me that their kinetic energy is lost. So that tells me it's not an elastic collision. The 2 objects do not stick together afterwards. They act like 2 different objects. So this is not a completely inelastic collision. So what we're left with in trial C is that this is an inelastic collision. All right. And right there, that answers the full question. You've identified all 3 trials, the types of collision, and you've given a physics reason why. And when you answer questions like this, if it's ask for a paragraph response, it is absolutely critical that you identify your answer and defend it with a physics reason. If you simply just say it's an inelastic collision and don't give an explanation, you will not get full credit. All right. Now, the second half of this question is not actually part of the FRQ. It's more of an exploration and a topic we didn't really talk a ton about. And basically what I want you to do is there's a collisions lab and it's linked on the Google Doc. If you can get it to run on your computer, if it's on your Chromebook, remember you just basically, if it says can't run Flash, just click to say run simulation anyways. What I want you to do is turn on the center of mass button. And I want you to imagine that this is actually measuring, if I was trying to balance the 2 little masses, the 2 objects I'm launching towards each other, that they have a center of mass. Now, for this particular question, this really doesn't mean a ton to us. It means a lot more for systems where you have 2 objects that are actually orbiting each other And a great example is a binary star system. So in some star systems, you have two stars that actually orbit each other. So they go around in a circle, and they orbit around their center of mass. So what that means is that even though the two of them are going in a circle, they act like they're orbiting around one big star in the middle where the center of mass is. All right. Now, the reason I bring this up in this question is because when you have, it talks about collisions or explosions sometimes, what it'll ask is it'll say, I want to know what the center of mass velocity is of this situation. And basically what you can look at is that the center of mass is acting like the two masses are just one big thing. All right. It's not particularly used for us right now. And if you honestly want more information on it, just Google it. Because I'm not particularly worried about being on the exam, but it's just something that if you've seen the question before, you understand at least at a certain point what's going on. All right. So with that being said, let's go to the fourth FRQ. So same deal as before, ladies and gentlemen. I want you to work through it if you haven't already done that. Hopefully at this point you have. So this particular question is set up as a lab question where you're kind of writing you're doing a little bit of writing to explain what's going on. Now, in any sort of lab question, you are free to use whatever equipment you can find in the classroom. So if you think a lab is set up and you could use something to measure a particular quantity, so let's say maybe you want to measure the time or you want to measure the force that the ball in this case hits the ground with, you are welcome to say in your answer, I use a force probe, I use a stopwatch. You don't have to limit yourself to whatever in the question. Okay? But with that being said, let's talk about what this is. Let's talk about this particular question. So all we have here is a launcher that can either launch up or launch down. Now, unfortunately, we can't see that because the whole situation is radioactive. So we can't actually see if the launcher goes up or goes down. We can imagine maybe we're behind a screen or something. But what we want to figure out is which way is the device set up. Now, what you can imagine too is that if it launches up, we move it, it gets moved out of the way before the ball comes back down. So don't just assume that it's going to hit the launcher on the way back down. Now, one student in the room is arguing that the only way we can figure out which way the ball was launched is that you literally have to watch the launch itself. So the only way we could tell if I launched it up or launched it down was to pay attention and watch the launch. Your task in this question is to basically say why they said that, and say if you agree or disagree, and then give your reasoning. All right. So for this particular question, we actually want to think about what are some things that either we know just by looking at the question or we could easily measure, because that might actually answer this question, make this question a little bit easier for us. So let's start by looking at what are some things it tells us. One of the things it tells us is it says the ball the ball is 0.5 meters above the ground when we launch it. That means that when all said and done, it's gone a vertical displacement, a delta y, of -5 meters, because that is how far away it is from where it started. Okay. Now, we also know a couple other things. As soon as that ball leaves the launcher, we know it is now in a state of free fall. So we know the acceleration is this. And hopefully you're starting to see where that I've already written down two variables. I'm starting to see that I can actually use kinematics and start to write some stuff down, because I'm starting to see these are all kinematic variables that I may or may not know. Now, I don't know the launch velocity, so I gotta leave that blank. I actually do know the final velocity because it tells me due to the motion detector what that is. And I might be able to use a stopwatch to figure out that last piece, the time. And if I know all those things, I can actually calculate the initial velocity of the launcher. Now, because of that, I can actually prove which way the launcher is going, because I can look at whatever the sign of this starting velocity is. Let's say if I launch it in the time using the time that I get, and I find that this is a negative value, that means it must have been launched downward because the starting velocity is negative. But if the time that I got when I used my stopwatch means that this starting velocity has to be positive, it means that I launched it up vertically. All right. So what my explanation basically says is it talks about first the idea that the student, you could say along the lines that probably the student thinks that you have to know which way it's launched because it's going to have the same final velocity in either case. And that is indeed true. And if you write down the energy, if you kind of write down the energy equation in each case, you'll see that they end with the same final kinetic energy. But we can say that you don't need to know the orientation, because as long as you can time how long it's in the air, you can work backwards and calculate which way it's aimed with the starting velocity. All right? So this is something where at first, I can understand you're looking at my explanation probably saying, oh, there's no way I'd ever figure that out. I promise you can. It goes back to writing down, if you're not sure where to start, write down things that you know in this question and see if it goes back to something that we've talked about before. In this case, literally, I just started writing down variables that I knew, and I saw that all of those related back to kinematics, and that's how I started to solve the question. All right? Now, the last piece of this FRQ is that now I've switched the launcher so it's launching to the right, and I want to basically compare its final velocity and its final speed compared to when I just launched it straight down. All right? Now remember, when we talk about speed, speed is literally the number. So that would be the equivalent of whatever the speedometer, if there was some magic speedometer in that ball right before it hit the ground, what it would read on it. Okay? Now, because of that, the speed part actually is no different, regardless of how I launch it. And it goes back to the energy discussion. If we have our thing being launched like this, or being launched, I'm sorry, it should be horizontally, being launched like this, or being launched like this. At the moment that it's launched, it has potential energy and it has kinetic energy from the launch. Now, when it gets to the very bottom, whether it's now here or it's now here, the only thing it has left is just kinetic energy. So regardless of if I launch it down or launch it to the right, according to energy, the equation is exactly the same. Which means if you solve for the final speed, you would get that the final speed of the ball in either case is going to be exactly the same. So the final speed of this ball is the same whether I launch it horizontally or straight down. The velocity question, though, is a little bit different. Velocity, if you remember, is not only dependent on the speed, but it's dependent on the direction that I launch it, or that it's going as well. Well, if I talk about the one where it's just launched straight down, all it has is negative velocity. And all it has really is a negative y velocity. But when we talk about the launch, when I've now launched it horizontally, now it not only has velocity in the down direction, because it's falling, but it also has horizontal velocity because I launched it that way. So in fact, the final velocity of the ball that's launched horizontally is going to be different because the direction of that velocity vector is going to be different. All right. So what it comes down to is honestly the speed, the number will be the same, but the direction it's going in will be different, which means the velocity is going to be different. All right. So with that being said, ladies and gentlemen, if you have questions, please send me an email. This is just kind of some great practice to see how the questions will be kind of set up on the AP exam. I'm going to post some more practice problems later on and some more practice FRQs. But with that being said, have a great rest of the day.